Um, so let us start with, I can see that you are less than 30 that are online now. Where are the other colleagues of yours?
We don't know.
You
So
don't know. Okay, so
I've shared the link to all the groups, and the only people that are online, I think, that join the class.
okay,
They will
okay.
eventually
So
join.
let's continue. Last week, so we want to start with the concept of isostasy. We said the word isostasy is a combination of two words from Greek, iso and stasis. The word iso means equal, whereas stasis means equal standing. So before I continue, the art, we said that the art is essentially in layers. And then you have what you call the crust, the mantle, and the core. The entire crust and the upper part of the mantle is referred to as the lithosphere. Whereas the remaining part of the mantle, especially the molten part of the mantle, is referred to as asthenosphere. The asthenosphere we said, add strong rigid plates, exert a downward directed load on the mobile underlying weaker plastic like asthenosphere. Let me see if I have something that I can use to explain that here. So here, last week, we talked about the asthenosphere. If you see what is here, the upper part, the entire crust, to this red one is part of the mantle. This red one is part of the mantle. From here to here is the crust. So the entire crust and the rigid part of the mantle, everything together is referred to as the lithosphere. Beneath this location is the asthenosphere, which is weak like a pap, is molten. So, and that the entire earth is broken into plates. The entire earth is broken into what you call
Sir. Hello, sir. I think you muted yourself.
So we can't hear you.
I think he
You
muted
guys should
himself
chill. Maybe he got the call.
by mistake.
Sorry, can you hear me clearly now?
Yes, sir.
Okay. So you can see all that you see. You can see Africa. This is water. All this area is water. All this is water. This is South Africa plate. And that is These are the things we call lithospheric plate. This is Arabian plate, African plate, North American plate, Australian plate. They are about them. These are the key features of those plates. The lithospheric plates, we said they are strong and rigid. It can float on the asthenosphere. The plates are mobile. They can move from one location to the other. So, and so on and so forth. So, having shown that, what is wrong with this thing? Okay. So last week we look at buoyancy. Now, we are now saying, now, let us now look at isostasy proper. We have said iso means the same. Statis means equal standing. Now, if you look at here, this is a mountain. And the lithosphere extends from here to here. This is the red part is the asthenosphere, which is molten. You can see this rock, as it's standing, shoot above the sea level. For it to be balanced, to be in equilibrium, is now sitting deep into the asthenosphere. So it is the lithosphere now, which we say is rigid, solid outer layer, and is brittle, strong crust, and the uppermost mantle, that is lithosphere. Asthenosphere, underlying denser, heat softened, partially melted material. So this lithosphere is now floating on the asthenosphere. So what you can see from here is that you can see this part where there is no mountain. The base did not dip into the asthenosphere. The part that has mountain, for it to be balanced, you can see that it has roots and deep into the molten asthenosphere so that it can attain equilibrium. You said do not confuse with crust and mantle, which are based on composition. The transition with lithosphere, that is, you should not confuse lithosphere with crust. Don't compare asthenosphere. Don't confuse it with the mantle. The lithosphere involves the entire crust and the uppermost part of the mantle, while the asthenosphere is the molten part of the mantle. Now, to be able to explain isostasy, if you look at this wood is longer than this one, and you put the two of them inside water, you can see that because this wood is longer, when you put it in water, you can see the part that is above water is more than this one. You now see that it has a significant part of it immersed in the water, more than this one, because it needs to achieve equilibrium. Equilibrium of adjacent blocks or brittle crust floating on underlying upper mantle, that is mapped above a certain depth, must be the same. Think of wood or blocks in water. Blocks that stick up higher, like this one, also extend further into the water so as to achieve equilibrium. The density of the wood must be less than the density of water for the wood to float inside water. For masses to be the same above the compensation depth, mass in column 1 must be equal to mass in column 2. Masses in both columns in two-dimensional equal density of wood multiplied by thickness of wood plus density of water multiplied by thickness of water. Density of water is greater than the density of wood. That is why the wood is able to float inside water. Wood that replaces water in the column must be thicker than the water it displaces. Wood that replaces water in the column must be thicker than water it replaces. So all that we are saying is that there is a depth we call compensation depth. That is the depth. If you start from the top to a particular point, this mass from the top to the bottom, if the mass, for instance, let's say is equal to 5 kg, from here to here is also equal to 5 kg. The depth at which the mass of this column and the mass of this column are the same is referred to as the compensation depth. So isostasy leads to isostatic adjustment if mass is redistributed. Now let's start that. Note that mountain and crustal root below it. Note mountain and crustal blue. You can see anywhere you have a mountain, the mountain will not just be, the bottom will not be flat. The bottom will mirror what you have. The bottom will mirror what you have on the surface. If mountain is like this on the surface, for it to be balanced, for it to be in equilibrium, the base will mirror what is in the subsurface should mirror what is in the on the surface. In a situation that equilibrium is not achieved, for instance, let's consider these two locations. X, denoted by this green box, and A, denoted by the purple color. When erosion occurs, the top of this mountain is eroded. What now happens is that the top and bottom of the mountain will not mirror one another again. Erosion redistributes rock from mountain high to sediment deposited in basin low. So less mass on mountain causes uplift of crust below mountain. Now, if you look at this one, you now see that erosion of this part of the mountain now occur, such that the base and the top no longer mirror one another. What will happen is that when this part has been eroded, the mountain will now begin to lift up in order to achieve equilibrium. The sediment that were eroded from here are deposited on the flanks. When the sediment are deposited here, you can see this white arrow. It means there is a lot of load on those two flanks here and here. Subsidence will occur. Because of the heavy load deposited here, this side will be going down. This side will be going down. The molten material will be redistributed. They will come to this side. This one will come to this side because this side is coming down. This side is coming down. Then it will cause this mountain to lift up. As this mountain is lifting up, you can see it was here before. But now that it's lifted up, it's now at this location. The top and the bottom are mirroring one another again. When mountain is going up, we call it uplift. That mountain is being, or you can call it isostatic uplift. When sediment are deposited on this side, you can see those two sides are going down.